For question number 12 here, we're asked to find the simplified average rate of change of this function between where x is 3 and x is 3 plus h. Now, it's an average rate of change. This is not a derivative. It's really a slope calculation. And so that's why there's no limit right here as h tends towards 0. So the reason it's a slope calculation is because these are really y values or function values we're subtracting here, like the rise in the slope formula, and the run, the horizontal distance between the x's, is the h value, because h is the difference between 3 plus h and 3. If we subtract those, we get h. Now to find f of 3 plus h, we put 3 plus h in the function. So it's negative 3 times 3 plus h squared, and that's what this is, plus 5 times, that's the 5 there, times the 3 plus h we're putting in place of x there, minus the 4, that's the 4 in the end, and then minus, so what's in the first set of square brackets here is the f of 3 plus h, and then f of 3 would be when we put 3 in the function, so 3 goes here, 3 goes here, and that's what it looks like in the second set of brackets here. Now, to calculate 3 plus h squared, it looks like this. So 3 plus h squared means two different 3 plus h's multiplied, and so 3 times 3 is 9, 3 times h is 3h, h times 3 is another 3h, and h times h is h squared. And then we combine like terms, 3h and 3h is 6h, so that's 9 plus 6h plus h squared. Now there's a negative out front here, so that just means we're going to change the signs in all these. That's why it's negative 9 minus 6h minus h squared. 5 gets multiplied in here. 5 times 3 is 15. 5 times the h is 5h minus the 4. And if we simplify all this, 3 squared is 9, so it's negative 9 here, and that's 15. Now, a whole bunch of stuff adds to 0, or some people use the word cancel out. So, for example, negative 9 take away negative 9 has to be 0. And so those are gone. Same with the 15s. 15 take away 15 is 0, and negative 4 take away negative 4 is also 0. So all that's gone. So all we have left actually is we have this negative h squared, and we have negative 6h and 5h would be negative h, and well, the 2's come from, the reason the 2 minus 2 is in here, I didn't actually, when I did this, do all that canceling out, but that's 0 as well. What this works out to be 2 in here, negative 9 plus 15 minus 4, and same thing over here as well. So those are gone. And so we're left with just negative h squared minus h over h, the h in the denominator. So that h will divide in. H goes into h squared h times. So there's a negative h here. And negative h divided by h is negative 1. So that's the average rate of change, whatever h is. So for example, if h was 1 and we're talking from where x is 3 to 4, then the average rate of change would be negative 2, because we'd have negative 1 minus 1 would be negative 2. For question number 13, the weasel population in hundreds in areas modeled for the next 8 years by this population function. And we're asked, what's the instantaneous rate of change in 2 years? So we would use the definition of the derivative formula. And so we're going to find basically p prime of t. So we put, we're going to calculate p of t plus h minus p of t, similar to f of x plus h minus f of x over h, and evaluate the limit as h tends towards 0. So we would put t plus h in place of time here. And so that would be t plus h squared after the negative 2, and plus 16 times the t plus h plus 5. So this whole part right here is the p of t plus h minus p of t. Well, this is p of t here. So that's why that's minus, is that minus there, and this is the p of t function. So similar to above, when you square the t plus h, it looks like this. So t plus h times t plus h, if you expand out and multiply them, you get this, which simplifies to t squared plus 2th plus h squared. Again, there's a negative 2 in front here, so the negative 2 gets expanded in, and that's why it's negative 2t squared minus 4th and minus 2h squared. Expand the 16 in here, that's that 5. Take the brackets off here, that negative is going to change all these signs. That's why these are all the opposites of what's up here. And then again, just like before, we get a whole bunch of stuff adds to 0. The negative 2t squared and 2t squareds add to 0. The 16t and negative 16t add to 0, as do the 5 and negative 5. And so we're basically left with this term right here. and then minus 2h squared, and then the 16h as well. And that's all over, of course, still this h in the denominator. Now, all of those terms divide evenly by h. So if we divide h into each of those, you get negative 4t minus 2h plus 16. And so we're taking the limit of that. It probably would be a good idea to put brackets around this. I didn't in the solution, but we've actually got a trinomial there, so it would be a good idea to put brackets around that. And so as h tends towards 0, this term gets really, really close, infinitesimally close to 0. And so basically it's negative 4t plus 16 is the derivative. And we're asked to find the instantaneous rate of change in 2 years. So we would plug 2 in place of time. So negative 8 plus 16 would be 8. And it says in the question that it's in hundreds, so it's actually 800 weasels per year it's changing at. It's positive, so it would be increasing at 800 weasels per year. And so what's happening at 2 years? So that's how it's changing. It's increasing 800 population per year. And so something that might cause that is perhaps there's less local predators in the area or a larger food supply, something like that. On to question 14. We're asked to find the following rates of change using a graphical method. And in A here it says the average rate of change from negative 5 to negative 2. So on this curve, at negative 5 is right here, at negative 2 would be right there. So this line here represents, the slope of it represents the average rate of change. And so the rise here is 3 and the run is 3 as well. So the rate would be 3 over 3, which is 1. So average rate of change between those points is 1. At an instantaneous at x equals negative 4, so at x equals negative 4, that would be the point right here, so we would try to draw a tangent line there. And so that's what my tangent looks like, and again we'll read the rise and run. So this horizontally is 4 units. If you count it vertically, this is 8 units from positive 7 down to negative 1. So the rate would be 8 over 4, which is 2. For question number 15, we're asked to use the first principle's definition derivative to find f prime of x for this function. So here's the definition of the derivative right here. And so we're using 2x squared plus 7x minus 3. So f of x plus h, we would put x plus h in place of x here and here. So it's 2 times x plus h squared plus 7 times the x plus h minus the 3. And then minus the f of x. This is the f of x here, of course. And so very similar to a couple of questions above, if you square x plus h, and actually here's the shortcut for squaring it, x squared would be x squared, and we're multiplying them by 2, so that's why this is 2x squared. H squared times 2 is 2h squared, and then x times h doubled, because when you're squaring there's 2 identical, in this case xh terms, so that would be 2xh times this 2 makes 4xh. So that's a shortcut for squaring. Multiply the 7 in here, you get those 2 terms, take the brackets off, all these signs change, so minus 7x and plus 3. And again, we get a whole bunch of stuff to add to 0. The 2x squareds, positive and negative are opposites, as are the 7x and negative 7x and negative 3 and positive 3. Not a lot left. Basically this term, and this term, which is what you see right here. And so h divides into both of those, all 3 of those, sorry. And so you get 4x plus 2h plus 7. As h tends towards 0, the 2h becomes exceedingly small. And so basically you have 4x plus 7 is the derivative. 9 to the power of x is the next one that we're going to differentiate. And so here's the definition of the derivative for h of x instead of f prime of x. And so the function is 9 to the x. And notice I'm using x plus s instead of x plus t. Okay, so I'm just using instead of h, sorry. So s is tending towards 0 in the limit. So the function is 9 to the x. So we would put x plus s in place of the exponent x, so this would be 9 to the x plus s. And then h of x is the 9 to the x function. And there's a common factor here. You can actually factor a 9 to the x out of both of these. And so the way you factor it out looks like this. So this is how the factoring goes. 9 to the x plus s. you can think of that as 9 to the x multiplied by 9 to the s. Remember, when you're multiplying two powers of the same base, you add the exponent. So x plus s would give you that x plus s right there. And so notice that there's a 9 to the power of x common factor in both of these. So that's why you can factor a 9 to the x out. And if you factor a 9 to the x out, what you're left with is this 9 to the s right here, and then minus 1, because when you factor a 9 to the power of x out of a 9 to the power of x, there should be 1 left. So that's why it's minus 1 in the end. So that's why this is here. The 9 to the x I factor right out of the limit because it's s that's tending towards 0, not x. And so by the definition of what this limit is, this limit would equal the ln of 9. And that's one of the givens that you're given in the course. You don't have to prove that. So the limit of 9 to the power of s minus 1 over s, as s tends towards 0, is the ln of 9. So the derivative is basically 9 to the x, the original function, times the ln of 9. And one last function, if you forget what it looks like, it's negative 5 over 2x plus 3 that we're differentiating here. And so I'm going to call it g of x. It's g of x in this case. So we're finding g prime. And so we put x plus h in place of x. Remember, it was negative 5 over 2x plus 3. So we put the x plus h in place of x here. And then this is the g of x function here. And what I've done from this line to this line is really just separate and put I was missing a sign here. I just noticed that. There should be actually a negative right here because the g of x function actually has a negative there. So if we expand out, let's look at this line here now. Now, if we expand the 2 in here, it'd be 2x plus 2h plus 3. And then the subtracting and negative same as adding, so there's a plus and then 5 over 2x plus 3 here. And in order to add these, I need a common denominator. So these two denominators actually have no common factors in common. So the common denominator is actually just the product of the two. So I'll end up multiplying this one by 2x plus 3 top and bottom, and this one by 2x plus 2h minus 3, plus 3, top and bottom, which is what I've done over here. So negative 5 multiplied in here would be negative 10x minus 15. And then plus 5 times this would be 10x plus 10h plus 15 here. And notice we get some stuff to add to 0. So the negative 10x and positive 10x add to 0, as does the negative 15 and 15. So that's why there's just a 10h left up in the numerator here. So 10h on top over that denominator all over h. And the way we evaluate this, we can't actually evaluate or think of putting 0 in place of h, although remember, h never actually equals 0. It gets close to 0. Is we take this and multiply it by the reciprocal, the h, which is 1 over h. And so that h will divide out with this h. Looks like that. And so what we're left with is 10 times 1, which is 10 on the numerator, over this product in the denominator. And as h tends towards 0, this 2h terms becomes 0, and so basically you have 2x plus 3 times another 2x plus 3, which is 2x plus 3 squared. On to question number 16. We are told that a certain bacteria culture starts with a population of 120, and that it grows to 5,000 in a day, or 24 hours. So we're asked to find a formula for the number of bacteria after t hours, and there's a couple of ways to do this. I'm going to show how it goes with the e function, but you could do the doubling function too if you want to make the base 2. So my population model will be P of t is the original 120 times e to the power of kt. We have to find what k is, and that's why you're given that the population grows to 5,000 in a day. So the 5,000 goes in place of the population, and the time is 24 hours. That's why 24 goes in place of t. I'm going to use hours. They're a little bit more convenient here than days. And so I want to solve for k here. So I would divide out the 120. And so the 120 is gone here. 5,000 over 120 reduces to 125 over 3. And so again, I'm trying to solve for k here. So e to the 24k would equal 125 over 3. So to put this back in its equivalent logarithmic or ln form, actually, the exponent, the 24k, would equal the ln of 125 over 3. To solve for k, then I would divide it to 24. So dividing this ln by 24, we get approximately 0.1554. And so putting that in place of k here, that's the formula. It's the population at any time is 120 times e to the power of 0.1554 times the time. So you're asked now how many bacteria there were after 14 hours. So we would just put 14 in place of time. And so the calculation would look like this. And so you get 1056.896. This is what it looks like in my graphing calculator. So there's the quantity. Of course, it's a number of bacteria, so you can't have a part of a bacteria. So we would round it to the nearest whole numbers, but about 1057 bacteria. For number 17, this is a radioactive decay. The last one was growth. A sample of radioactive plutonium started with 16.2 milligrams, and we're told this isotope's half-life is 2.7 hours. Now, this is another time where you could use the model with 2 as a base, or half if you wanted to. Okay, that would work as well. And I'll actually show that in that's why this says solution 1 here on the next page. So I'm going to call n the amount of plutonium at any time. So it's 16.2, the original amount, times e to the kt, and I need to again solve for k. So we're told that it goes down to it goes to half in 2.7 hours. So half of 16.2 would be 8.1. So 8.1 would be the amount after 2.7 hours. And so I would divide out the 16.2, so that works out to a half, 0.5, would equal e to the 2.7k. And so 2.7k, putting this in the equivalent ln form, would equal the ln of the 0.5. And then we divide out the 2.7. And so you get negative 0.2567. So the formula would be n of t is 16.2 times e to the power of negative 0.2567 times the time. In B, it says, how long will it take for the sample size to be down to just 1 milligram? So in place of n of t, that's the amount. So we'll put 1 milligram there and solve for time. So dividing out the 16.2, those divide out, we would get e to this decimal as 1 over 16.2. And then divide out, get the exponent here alone. Solve for the exponent here. So negative 0.2567t, putting it in the equivalent ln form, would equal the ln of this fraction. And so dividing this decimal out, we get the ln of that 1 over 16.2 divided by 0.2567, and there's the negative right there. I don't actually have it in the denominator, but there is a negative there. And that should work out to 10.85 hours. Now, this is the second option here. Another way to do this is instead of using the base of e, you could use, a half or 2 if the exponent's negative. If the half-life is 2.7 hours and starts at 16.2, there's really kind of a canned formula here. It's 16.2 times 2 to the power of negative the time over the half-life, or if you wanted to instead write it as, you could write it like this as well. So that's an okay way to write it too. Remember that a half to the power of 2 to the power of negative 1 is the same as a half. So that's why these are equivalent. So that's another way to write that. To solve question B, we'll use this form and put 1 in place of n of t, and you can work through all the math here. You again get 10.85 hours. The solving is quite simple, quite similar, to the first one. And I think we'll stop there. We'll continue with 18 in the second part. Next part.